All right, you guys, a couple new readings, section 10.3, section 11.1. Those readings, 10.1 through 10.3 and 11.1, will provide you everything, all of sort of the syntactical and big idea stuff for homework 6, which is to write the fraction class. Let me show you really briefly what I mean by fraction class. Let's go here and here and here. Oops. So I think the TI-83s, those calculators you buy in high school, graphing calculators, I think they do fractions. Is that right? Yeah. So what I mean by fractions is instead of just immediately jumping to a decimal representation of a fraction, what you're going to do is preserve the fractionness, right? So 2/3 plus, 3/5, and it's going to give you back a fraction. What I'd like to do is, or what you're going to have to do is write a fraction class that essentially preserves the fractionness of a particular number. So it's going to have a numerator, it's going to have a denominator, and it's going to have a sign. And you're going to teach your class how to represent fractions, how to reduce fractions, how to add, subtract, multiply, and divide fractions. And just to demo what I mean, you're going to be able to do things like, for example, in this little main program here, this main program includes the fraction definition, or declaration, sorry, includes the fraction declaration at the top. And then what this gives me is access to the fraction data type. And this is a data type that I wrote. This is what you will write. And you will declare variables, objects in that class. For example, this guy here, fraction f12 true, defines the fraction -1/2. The first argument is the numerator, the second is the denominator, and the third is the sign, S-I-G-N, of the fraction. When the sign is true, that means there's a sign. And when it's false, it means there's not a sign. And then this guy down here, fraction s, is just a third fraction that lets me hold results, for example, as I test my class. You, when you write this thing, are going to turn in really just one file. It's going to be called fraction.cpp. And what I'm going to do is take your fraction.cpp and my fraction.h and my main.cpp, and I'm going to mush them all together, and I'm going to run them. And they're going to test every possible aspect of the class that you wrote. And I'll be able to just scan down this list of tests, and if I see a problem in one of them, then I'll be able to dive in to your class and figure out where you made a mistake or something like that. So you will not be writing a main program for this next assignment. You are simply going to write the functions associated with this class. How do you add two fractions? How do you subtract two fractions? How do you multiply? How do you divide? And then I will write a main program that multiplies using your multiplication function, or adds using your addition function, and make sure that you get the right, that I get the right answers. Let me show you. Let's just keep it simple here. Let's take two fractions. Both of them are going to be +1/2. And I'm just going to add them together. So the add function is something that I wrote, and it takes two fractions and adds them together and returns a fraction, which then ends up in s. And then the print function is something that I also wrote, and when I say s.print, it prints itself to the screen. Oops. So there, that's great. 1/2 plus 1/2 is 1. I could change the sign on one of these, and then I should get 0. And it looks like I've still got some work to do on my class, but you get the idea. I could take, say, 1/2 plus 1/3, which should come out to be 1/6. Oops, keep doing that wrong. Sorry, 5/6, yes. Having a good math day today. All right. Or I can change the sign on one of these guys. This should come out to be minus 1/6. Yeah. So what's producing the negative 1/6 or the 1 or what have you is this command right here. Again, this is a much more abstract programming assignment than you've done up to this point. You're not going to give me a program that I run and it's going to do something. You're going to give me a framework, a collection of functions that defines what it means to be a fraction, and I'm going to test and see whether you have correctly written add, correctly written multiply, etc., etc. Okay, so that's a demonstration of the fraction class. We're going to have a presentation from Eric, who's going to talk about who invented HTML and what is it good for. And then, in fact, I think we'll maybe do that right now, Eric. So why don't you come on up? And then after he's done, we're going to continue the complex example that I started on Friday with an idea towards applying some of that stuff to the fraction class. And then I'll discuss the fraction class a little bit more as well. Okay, how many people are going to be here Friday? That's what I like to say. I'll be here. Let me know when you're ready, Jerry.
Right. 1 second. All right. Okay, I'm going to talk about HTML today. I'm going to say what HTML is, who invented it, and what it's good for. Okay, what is HTML? HTML stands for Hypertext Markup Language. It's an authoring language used to create documents on the World Wide Web, which is WWW we use now. And it's mainly used to define the structure and layout of a web page, how a page looks like, and any special functions. And the inventor of HTML is Tim Berners-Lee. He is a British computer scientist who graduated from Oxford, received a degree there in upper level physics, and he is the director of the World Wide Web Consortium now. That's the group which set up the technical standard for web, and we can see a screenshot here, like how we developed first version of HTML. Okay, this was a true browser editor for the first version of HTML. He worked on that on a Next station, which he bought in the CERN Center, which is an international organization of scientific, it's like a nuclear research center. And he worked there and invented the first version of HTML. And the first version of HTML was formally published on June 1993. Okay, so what is HTML? The hypertext stance is the text displayed on computer and or other electronic device with reference, or called hyperlinks. That means you can any text in that links you can immediately access by just using a mouse click, or you just touching the screen or keyboard input. And it's the underlying concept of defining the structure of the World Wide Web. It enables an easy to use and flexible connection of information over the internet. Then markup language. The markup language is not equal to a programming language. It's not a programming language. What it's used for is it's a combination of words and symbols which give instructions on how a document should appear. For example, you can use a markup language to tell the computer how you want to write a word. You want to put it in the italics form or to bold type. Yeah, that's the example. And the HTML is a markup language which encloses and marks data with HTML tags. They define the data and describe its purpose on a web page. So how does that really work? There are three main sections of web documents: the head, the title, and the body. The head pretty much including a website's title and important keywords, such the viewer sees the website, but any other information is hidden. The body section is the main portion of a web page visible to the user, but including the text and graphics. So the HTML pretty much describes the data to the browser, and the browser then interprets it and displays the data accordingly. It's only used for structure purpose, not for function purpose. So it's only for to structure a layout or something like that, not tell computer what to do or how to program it. Yeah, this is a screenshot of a program language, HTML. You can see the head there. And these meta tags is used for, these meta tags that indicate keywords associated with the web page to search engines. And you can see head there and body part there. So besides HTML, there are some other language like LaTeX or XML. These are also markup language, but HTML is like most widely used. But why HTML? There are several cons, several pros of HTML. The first is very easy to learn. It's really simple in heart. There are only a couple dozen of tags, but less than half of them are mostly used. It's very cheap or sometimes free, but it's very powerful. It can come with a combination of third-party add-ins and server-side content support. HTML document browser interface are really easy to build into existing products because it's simple and it has high simplicity, so you can easily to plumb these existing products into HTML documents. And last but not least, HTML links really does work across multiple systems, and even though they're otherwise unrelated, any page can link to other public accessible pages simply by just entering the address. And this is a picture of the latest version of HTML5. All right, any question?
Did Tim Berners-Lee write the first web browser also?
Yeah, I think so. Okay. Yeah, with his colleagues.
Oh, so if it's not a markup, like if it's not like a programming language, does it do a similar thing to get converted into something that the computer can understand? Like I'm curious about, so does the computer just, or the whatever you're feeding it into, just understand like what you're inputting is going
I think
to
there's also a
create?
compiler to do that.
Well, that's the browser, really.
That's the browser,
right?
okay.
So, how many of you guys have written in HTML? Any of you? A few? Like you'll put, you'll have a word that you want to emphasize, right? So italics. You'll put a tag around it, and as the browser reads through your HTML, it's going to see emphasize. Oh, it's going to change the font automatically to italics, and then it's going to see the end of the emphasize, and it's going to turn that font back to it. So it's not really compiled ever.
LaTeX, and that's the way like.
LaTeX compiles, and there are technical reasons why LaTeX compiles and HTML doesn't, which we won't go into here. So they are slightly different. But LaTeX is probably closer to a markup language than it is to a programming language.
That's what I was. Yeah.
But in fact, LaTeX has if statements and loops and things like that, which is why you can compile, where HTML does not have if statements and loops and so forth. So,
Okay.
Yeah. Okay. Thanks very much. All right, you guys. Let's. Shocking. Okay. And Tim Berners-Lee, I think, has been knighted by the British royalty. This is the 270. I don't want 270. I want 167. There we go. All right, I want to continue my example. Last time I kind of got, well, perhaps for lack of a better term, I kind of got mired down in the arithmetic of complex numbers. But it was necessary, because what we have to do before we can actually write a program that will add and subtract and multiply and divide complex numbers, we need to have formulas to do those things so that we can program them into our class. So I left last Friday with the beginnings of my complex class. This part up here is going to be the name of the data type, or the name of the class, complex. And then the complex classes are divided up into two sections. There's a private section and a public section. And the things that are private can not be accessed directly by the programmer, whereas the things that are public can be directly accessed. And before I get into more detail about private and public and classes and so forth, it should be emphasized that when a computer scientist designs a programming language, like, for example, when Bjarne Stroustrup designed C++, it's as much a psychological exercise as it is a technical exercise. What Stroustrup is trying to do is write a language that helps programmers be better programmers. Because humans are not really naturally adapted, as you may be discovering, naturally adapted to programming. The level of detail and the potential for errors are just everywhere at all steps of the programming process. And so a good compiler designer, a good language designer like Bjarne Stroustrup is trying to help programmers be better programmers. So he decided that it would be good to be able to merge data together with functions, and he also invented this paradigm of public and private sections to sort of further compartmentalize the data and the associated functions. So this helps a programmer think about algorithms and how to organize programs. So there's nothing sort of intrinsically necessary about having classes and having public and private data and member functions. All of the stuff that we do in this class in C++ can be done using C or Pascal or Fortran or any so-called Turing-complete programming language. It's really just how the designer of the language thought it would be best for programmers to program. So, with that in mind, let me show you how these classes work by continuing this example of complex numbers. So, what I'd like to do is develop my own data type called complex that will, in some sense, faithfully represent complex numbers as we understand them mathematically. Okay, now that we're writing classes, it's time to introduce the notion of separate compilation. So I'm going to show you my declaration. This is how I declare a class. It's very similar with what I wrote on my notes. Let's forget about these two guys for the moment, but the name of my class is going to be complex. And the things that I can access in my class are in the public section. For example, the absolute value function will return the absolute value of the complex number. The conjugate function will return the complex conjugate of a complex number. The print function will print the complex number, and so forth. Ignore these friend functions for the moment. And then down at the bottom is the data that represents the class. And they're really just two variables, the real part and the imaginary part. And I've decided to call them private, and that's traditional when you're writing a class. The class variables, the stuff that actually holds the data, is normally declared private. All right, so that's the header file, the .h file. We have to start talking about the notion of separate compilation. And I am recording this, so you might want to come back and sort of watch this again, just so you get it in your head. Remember when I first taught you about functions and I said, okay, you declare the function up at the top above main, and then you define the function down below main? This is the next step in that process. Now what we're doing is we're declaring the class in a file called complex.h, and we are going to define the class in a file called complex.cpp. So it's in here that I will explain how I'm going to add complex numbers, how I'm going to divide complex numbers, etc. In order to make this thing work, I actually have to include the definitions. The declarations. This declares the complex class by simply reaching out, grabbing that file, and putting it into this file. So it's very similar to when you write a function, you declare it at the top and you define it at the bottom. The same thing is happening here. You're declaring it at the top, and now you're going to define at the bottom. So this is a step-by-step process. We'll just build up one function at a time. Let me look at the complex.h file here. So the first thing that's in my class is something called a constructor. And this guy is responsible for doing things when you declare a complex number. For example, I'm going to choose to make it so that whenever somebody declares a complex number, the real and imaginary part are set to 0. So this guy, which will run when I declare the complex number, is responsible for setting the real part equal to 0 and the imaginary part equal to 0. And then I'm done. So whenever I declare a complex number, internally that data will be set to 0. If I don't do this and I declare a complex number, I'm kind of back in the uninitialized territory. I don't know what I'm going to have in the real part and in the imaginary part. And so this is a design choice. I am deciding that whenever a user declares a complex number, it's going to be set to 0. Just for the sake of presentation, I'm also going to define the print function so that we can print out the contents of a particular complex number. So as we work, we can see what we're doing. But it's not going to be a very nice print function. It's just going to print out in ordered pair notation the real part and the imaginary part. Like that. And since I'm using cout, I'm going to have to include IOStream. And I'm also going to have to do using namespace standard. Okay. I know what your question is, Emily. Go ahead.
No, you can answer.
Are you wondering about the double colons?
I was wondering about it. Yes, but the choice of the word before the double colons, does it have to match?
Yeah. Okay. Yes. So this is an important syntactical point. The double colon has a really fancy name, but don't let it scare you. It's called the scope resolution operator. And what it says is this function here that I'm defining, complex, is part of the complex class. And it's necessary when you separate the declaration of a class and the definition of a class, which is what I'm doing. You could alternatively, and it's just not done, but you could define the function at declaration in here, and then you wouldn't need that scope resolution operator. But we are not going to do that in this class. We're always going to separate the declaration and the definition of our classes. So I've got enough here actually to compile and run but I don't actually have a main function. So this leads me to the third of our triumvirate. So now I'm going to make a third file called main.cpp, and I'm going to include complex.h, which will let me use complex data types. And with that inclusion, oh, and notice the double quotes versus the angle brackets. Double quotes refer to header files that are in the current directory that you're working on, and the angle brackets mean go out and look for this in the system directory. Let me make a note of that. So in both cases, the include statement is looking for a file to include in your program. The angle brackets mean go out onto the system and find it, and the double quotes mean this is something that I wrote and it's in my folder. Use that. I am now able to declare complex numbers. Let's call it Z, and print out a complex number. All right, now one more thing. How do you actually compile this thing? Well, it's actually not that bad. G++ complex.cpp main.cpp, just like that. And what it'll do is it'll compile both of the files and mush them together into a single executable. Everything went well, and now there's an a.out. And if I run a.out, it prints out 0, 0, which is what we expected, right? The constructor built the complex number, set real part to 0, imaginary part to 0, and then it printed itself, z.print. Still with me? All right, if you go to the class web page and you look at the assignment, I have given you fraction.h. So you don't need to cut and paste. You can just right-click on this thing and download. Although you are working in a terminal, so maybe you do have to cut and paste. Or you can use links. Yay, links. Another file that's here is the makefile. What this is a way of automating the compilation process. So you can just copy this as is, and it will copy the contents into a file called makefile. And what that lets me do, whenever I want to make whenever I want to compile, I can just type make. And when you're dealing with lots of separate files, like 3 separate files here, make is definitely the way to go. It makes life easier. No pun intended. All right. The other thing is, if you're working in any one of these files and you type make in VI, Vim understands make, and you can type make and it'll rebuild the program for you. So you can actually make the new executable from within VI. All right. Let me just really emphasize here the difference between public and private. Let's pretend that I made real and imaginary public, and there's no private section. So I can rebuild this thing, and you'll see that it behaves exactly the same. There's no difference. Let me show you what public and private means explicitly. Instead of printing, let's pretend now that I just do cout z.real and then z.imaginary. This should also continue to work. Okay? Now let me go back to complex.h and put private back in there. And then I'll run make. So now I get a compiler error, and it's saying, you know what? The variable real is private. You're not allowed to do what you're trying to do on line 15 of main. So you go to line 15 of main, and what you're not allowed to do if these variables are private, and you can have private functions as well, is you, the programmer who's using the class, you're not allowed to access that stuff using the dot operator. So it's a way of compartmentalizing the stuff that you want the programmer to be able to access and the stuff that you don't want the programmer to be able to access in your class. Because this is a really simple class, but some classes are terribly complicated. And the internal data is extremely delicate. And so you don't want somebody who's using your class to sort of reach in there and change one variable because they happen to know it's there, and then the whole thing falls apart. It's just a big disaster after that. So this lets me protect data that shouldn't be changed by the user of the class. Carter, did you have a comment, question? Okay. So again, this is very much about psychology and philosophy of programming, not something that is critically necessary to writing a program. None of this public-private stuff matters when it comes to writing a piece of code that accomplishes a specific task. It's really about a philosophy of programming that Strustrup is trying to emphasize. So now that I have made real and imaginary private, the only way that I can print out and see the contents of the complex number is to do what? Use the .print function. The print function is a member of the class, and the print function is allowed to access the private data. But you, the user of the class, you're not allowed to access the private data. So now we're back to where we started. We recompile, we run, and everything is lovely. The idea is that as I build my class, I control how you access the data. So if you want to see the contents of the data, you don't get to just reach in there and grab out real and grab out imaginary. You have to call my print function to see that data. Questions? Go ahead.
Could you repeat what the make function does exactly?
So remember when I went out here and I just compiled manually, right, where a G++ complex CPP? The make program, it's actually a totally separate program. It's like out there on the system. What's really cool about make is if I make a change to main.cpp and I don't make a change to complex.cpp, it's smart enough to just only compile main and then make a new program. Or if I make a change to complex but I don't make a change to main, same thing. So this program will actually keep track of the changes that you've made and only compile the stuff that it needs to compile. And for a little dinky program like this, that's really hardly any kind of savings at all. But for example, the operating system that I'm working on in this computer, it's the Linux operating system and it runs in the Linux kernel. And if you want to compile the Linux kernel, it'll take about 30 minutes on a standard computer. And if I'm a programmer and I'm working on the Linux kernel and I go in and I make one change to one stupid printer driver file, I don't want to recompile the whole kernel. I just want to recompile the piece that I changed and then make a new executable. And that's what make allows. So make is a production level utility for people working on large projects spread over hundreds and hundreds of files. And if I make one small change in one file, it'll compile that guy and then not bother to recompile everything else because there were no changes, and it's much more efficient. If you ever have a question about make, by all means, just ask me. But right now, I'm just going to treat it as a utility and provide you the makefile so that you can make this a little bit easier. If you're ever stuck, also your makefile is not working, you can always just do this. And that'll get you the same place. Let's look at some of the other. All right, so this is syntax that you just essentially kind of have to follow. The constructor is a weird function. The constructor always has the same name as the class. Usually it's near the top, and it has to be public. You can have more than one constructor. For example, it might be convenient for me to not only declare a complex number at the beginning, but to give it certain values. So I'm going to now write a second constructor. And I'm going to give it 2 arguments, a real part and an imaginary part. Oops. So what's going to happen inside this function? It's very simple. What do you think is going to happen? How am I going to define this function? Just guess. No guess is a bad guess. So I'm the programmer, and I'm providing R and I. What do I want to do with them?
Real equals R.
Exactly. And that's it. Most member functions are usually pretty simple. So I've made some changes. I'm going to make. Looks like everything's good. Let's go into main and actually test this thing. How can I test this new constructor that I just built? So this is something that happens at declaration. I'm just going to give it 2 numbers. Right? That's what the new constructor does. Instead of making a complex number that's 0, 0, it makes a complex number that's 1, 2. If this thing is functioning correctly and I run it, I should see the complex number 1, 2 get printed out. So let's remake and run this thing, and it does appear to be working. And I can make more than one complex number. And I can print out more than one complex number. I can have as many complex numbers as I want. I can have an array of complex numbers, and with different values in the constructor, I can build them to have different values. If I'm tired of this particular complex number and I would like to have a different complex number in there, I can do something like I can overwrite it with the constructor. All right, questions about that? There's a difference between z.print and z equals complex, right? This is actually calling the constructor of the class to create a new object and put it in z. This guy is calling the print function of an existing object, one that's already been declared and already has values in it. Let's add another function. You know what else is nice about this as I'm building this class up? I don't have to have everything in my class defined in order to use it. So it's really nice for someone who's building a class from scratch. You can have these things right now. If I call z.abs, it's going to probably crash or it won't do anything because abs is not defined yet. But the nice thing is, as long as I don't use it, it's not going to give me an error. But let's go to that next one. Let's define that guy. So I'm going to grab that and go over to complex.cpp, and I try to preserve order, but it's not really important that you preserve order. The absolute value of a complex number, it's actually one of the formulas that I didn't derive. The absolute value of a complex number, let me just sketch it out here for you. You'll remember the geometric definition that I gave you for a complex number where you go out a distance a along the real axis and then along a distance b along the imaginary axis, and that gives you a point. The absolute value of a complex number is just the distance to the origin. So can you think of a formula for the absolute value? Yeah, the Pythagorean theorem, right? That's a right angle right there. One leg is of length A, the other leg is of length B. And so the absolute value, which will denote vertical bars, is just the square root of A squared plus B squared. So we're going to need that formula as we write the absolute value function. So return the square root of real star real plus imag star imag. And again, as I mentioned, a lot of the member functions are pretty straightforward. So it grabs the real part, squares it, grabs the imaginary part, squares it, adds them together, square root, returns it to the calling function. It's going to yell at me about the square root function, so I'm going to include cmath up here. Let's see if that compiles. It does. Let's go to main and test. So now what we'd like to do is make sure that that our absolute value function is working. We're pretty much satisfied with the constructors at the moment. How can I test the square root function? Sorry, the absolute value function. Yeah. So we'll do cout. Let's do W, right? Because that's that one we know. What's that going to be? 5, 3, 4, 5 triangle, right? So if this thing is working, we should get 5. And it is. All right, let's keep going. I guess we could try it on 1, 2. I don't know what 1, 2 is going to be. Is that going to be like the square root of 5? Whatever that is. I buy that. All right. Let's do the next one. So we're going to now write the complex conjugate function. The complex conjugate function takes the complex number and returns its conjugate. Does anybody remember what the conjugate of a complex number is? A plus IB, the conjugate is A minus IB. So what I need to do is build and return a complex number that is of the form real, negative, imaginary. Use the constructor, the 2-argument constructor that we already built. That's totally fair game. This guy will build a complex number whose real part is the same as the current complex number, and whose imaginary part is the negation of the current complex number. It'll build that complex number and then return it to the calling function. So let's see what that looks like. So if z is 1, 2, w we don't really care about. Let's let w equal z dot conjugate. Remember what z dot conjugate does. It builds a new complex number that is the complex conjugate of z and returns it to the calling function, which then gets assigned to w. So when we print out w here, in fact, we'll print out both of them. So we're going to print out z equals z.print, and then we'll do an end line, and then we'll print out w equals w.print, and we'll see out the end line. And hopefully what we'll see is 1, 2, and 1, negative 2. Line 28. Doing something silly here, but I don't see what it is. No, it returns a complex.
How do we call it complex conjugate here, but then we just call it conjugate?
Okay, well, if you go back to the header file, the function is called conjugate. It's sort of like print, and the return value is complex, and that's the problem.
It just doesn't.
And I just figured out the problem. Yes. Thanks for asking me that. Oh, that we want to keep. No. There we go. Okay, conjugate is a member of the complex class, and the return type is complex. This will fix it. And there you have 1, 2, and 1, negative 2, which that's behaving correctly. Almost out of time. Let me do one more. Well, these guys are all done. Let's talk a little bit about friend. So these guys, typically we put them in the public section, but they are not members of the class. These guys are functions that are allowed to muck around with the private data. What do I mean by that? Let me do add for you, and then we'll talk more about it next time. So I'm going to go over here and define add. And you're going to notice that there is no scope resolution operator. This is just a function called add that takes two complex numbers and returns a complex number. Oops, I have to give it arguments. Z and W, say. Now, this is not a member of the class, but the add function has permission to play around with the private section of the object. This is a matter of convenience more than anything else. So but by forcing the programmer to declare the function a friend of the class, you kind of make the programmer think about the whole public-private paradigm, and the idea is it adds a certain level of awareness to the programmer and what they're doing. So this should take two complex numbers, z and w, add the real parts, add the imaginary parts, and return a new complex number with those particular parts. Let's go over here and test. Let's do let's make a third complex number. And I'm going to let x equal the sum of z and w. And then we'll print out x. So z is 1, 2, w is 1, negative 2, and the sum is 2, 0. Every time I add a new member function, my class gets a little more capable, a little more sophisticated. And next time we'll do we'll do multiplication and sort of finish out the class, and then I'll review how you do this for the fraction class.